Okay, so this chapter is on energy and metabolism. And the first section, we're going to look at the flow of energy in living systems. And your learning outcomes are going to be to differentiate between kinetic and potential energy, and then to identify source of energy for the biosphere, and then describe the nature of redox reactions. Okay, so the first thing we're going to look at is an area of study called thermodynamics. And thermodynamics is a branch of chemistry. It involves a bit of physics. And here we're going to concern ourselves with the energy changes that take place. And so the big idea here is that living systems cannot violate the laws of chemistry and physics, and that's true of cells, which is a living system. And so let's define energy here. And so energy is the ability or the capacity to do work. There's two states of energy. We've probably heard them before in our science courses before. So there's kinetic energy, which is the energy of motion, moving parts, and then there's potential energy, which would be energy stored that could be used to do work. And so there's many forms of energy. There's mechanical energy, which is the energy of moving parts. And then there's heat. But I think a better word to use there would be thermal energy. Okay. Because thermal energy is basically a measure of energy of small particles, like molecules. So molecules are often moving around in random direction, like in the air you're breathing. The oxygen and so on are moving in random directions, colliding with each other. So these particles have kinetic energy, and that total energy is thermal energy. And thermal energy flows from area of higher energy, average energy of those particles, to lower. And you might think of that as wherever they're moving faster, it's warmer. The temperature's higher. And so when those particles are moving faster, they collide with those moving more slowly, and that energy gets transferred there. That transfer of energy from higher thermal energy to lower is called heat. So heat is actually very specific, meaning the flow of that thermal energy. But it's energy. And then we have sound. There's electric current, light, and radioactivity are all different forms of energy. There's going to be a convenient way to measure energy for us, and that's measuring the flow of that thermal energy or heat. You might have heard of the calorie before. The calorie is a unit of energy. And in some of the other physical sciences, they use a smaller unit called a joule. So one small calorie is going to actually has a relationship is equal to 4.184 joules. So you may see joules used. It's actually a smaller unit. It takes a little over 4 of them to equal to 1 calorie. Now they are defining what's called a small calorie, and it's the energy, the amount of heat energy that would be required to raise 1 gram of water by 1 degree Celsius, right? So 1 gram is equal, it's the same as 1 milliliter when it comes to water. So 1 milliliter water raised 1 degree Celsius would have had to absorb a calorie of heat energy, right? If it goes up 2 degrees Celsius, then 2 calories were added. And that's different from the food calorie that you see on your food packages. It's with a capital C, and it's actually equal to a kilocalorie, and kilo means 1,000. And so when you look at this bag, like the label on a bag of barbecue chips here, it says 160, but these are food calories. So really, it's 160,000 small calories, right? What that means is there's enough energy in that bag of chips that it can raise 160,000 milliliters of water by 1 degree Celsius. So that's a significant amount of energy there. So here we have a mechanical system and mechanical energy here on a playground. You have a child that's done the work of climbing up the ladder, and what she's done is increased her potential energy with respect to the ground. That's called gravitational potential energy. And she has a certain amount of gravitational potential energy up there. And when she goes down the slide, that energy, the potential energy, is going to turn into the energy of motion, kinetic energy, and so it'll convert. And so now she's moving, and a moving mass like her body there would have kinetic energy. So there, the potential is being transformed into kinetic energy. Okay. So energy does flow, and you can't recycle energy. So never say we recycle energy. You can recycle matter, but not energy in living systems. So energy does flow. It's one way. And that's a big difference. And for most ecosystems, they're going to start with the sun. So you have sunlight, bringing in your radiant energy, electromagnetic energy, And then that's picked up by plants. So you have plants growing, they're harvesting that energy and using it to build biomolecules, to build biomass, right? And then you can have animals, some kind of animal here, a herbivore, maybe a cow or something that's eating the grass or whatever. And so energy ends in that way. So we start with the sun, and then we go to photosynthetic organisms like your tree there, your plant. And then that tree is going to build biological molecules, build biomass. And there's going to be potential energy stored in those bonds. So there's potential energy in the wood, right? You can burn wood and it makes a fire, gives off heat. That's the energy of the bonds in that biomass that was built by the photosynthetic organism. So anytime that we're talking about building and breaking down compounds, building up like biomass, breaking it down, that's going to involve transformations of or transfers of energy. Okay, so generally when you're going to break bonds, you're going to need to put energy in there because the bonds are there for a reason. There's a relative stability there. So always got to remember there's energy needed to break bonds. Okay, so sometimes energy is going to be required, maybe necessary to help make new bonds. And then when the new bonds are formed, during that new bond formation, that process is going to give off energy. It's kind of like you separated atoms. They're going to be more stable if they're together to make this new bond. It's kind of like if you climb a ladder and then you jump back down to the ground. When you're coming back down to the ground, you're going to give off energy in the form of kinetic energy. When those atoms come together, energy is given out. So it requires energy to break bonds, and then the atoms shift and find new ones, and they come together. And when they do, when they're making that new bond, they give off energy. So you gotta put in energy to break bonds, and then new bonds being formed gives off energy. So we'll look at those types of things in more detail in a little bit. Okay, so all chemical reactions that take place when you're making bonds, when you're breaking bonds, making new compounds, they can all be classified as redox reactions. And that's short for reduction and oxidation, kind of backwards the way it's written here. And when it comes to oxidation, okay, when it's an oxidation, the one particle or molecule is going to be losing an electron. So when you lose an electron, you're oxidized. Okay, so that's the oxidation. And the other one is going to gain that electron. So when it gains electron or electrons, that's reduced. So they have a very simple model here. Let's say that particle A could be an atom, could be a molecule. Right now it has neutral. It's got a balance of protons and electrons. We made of many atoms. Atoms have nucleus that are positive, and the electrons overall, the positives are balanced with the negatives. Same over here. So we're going to put 0, 0, understood, neutral. Now let's say during this chemical reaction, A loses an electron to B. Okay, so we see that from A, an electron is moving to B there. And so you end up with one less electron than what balances you out. So you now have a positive charge here indicated right there. And B gained an electron, so now it's negative. Okay, so now the idea is, okay, well, which one was reduced? The one that gained the electron. Okay, so that's something to remember. The one that gains the electron is reduced. The one that loses it is oxidized. Okay, and so this kind of oxidation reduction is pretty easy to follow if we use the simple modeling that we saw back in chapter 2, where we draw dot structures. We draw dots just to represent the valence electrons, right? And so here, if you have sodium, it's a metal that has only one valence electron. And chlorine is in the second to the last column. It's going to have 7 valence electrons. I need one more to get that octet. During the reaction here, the metal loses its electron to chlorine. So just draw a little arrow going right there like that. And that's going to give you now sodium that's missing 1 electron. So it's got a plus charge. And then the chlorine gains that extra electron, and now it's got a negative charge. The chlorine gained that electron, it's the one that's reduced, because the one that gains is the reduced one. The one that lost is oxidized. So it's pretty easy to follow. There's some other terminology here. So the one that gained is reduced. The one that gets reduced, though, is referred to as the oxidizer. because it's oxidizing the other one, right? The sodium gets oxidized, it's oxidized by the oxidizer. So in case you see that, you want to make sure you play around with these terms so you don't get them confused. The oxidizer is also called the oxidizing agent because it oxidizes the other one. Okay. The other compound or particle, in this case just an atom, is called the reducer because it causes the reduction of the other one. Remember, when you reduce, when you become reduced, you're gaining electrons, so the reducer is the one that's going to give up the electron, right? So to be oxidized is different than being the oxidizer. The oxidizer causes the oxidation. Now, these reactions are always going to occur. They're always paired. You cannot have a reduction without an oxidation. Okay, the reduction, that electron has to come from somewhere. Okay, so we can draw just the sodium. Okay, and we can draw that sodium being oxidized. Okay, it's been oxidized right there. But you can't have that unless you have something else being reduced. So you can draw your chlorine going through its reduction. It's got 7 electrons, and then becomes reduced. And so these are two separate things going on, but they're connected. You can't have one without the other. This electron here can't come from nowhere. You can't just create an electron. Charge is conserved, just like mass is conserved. Now, there's something else to consider when we're going to be looking at a lot of different chemical reactions that occur. Some of the important metabolic pathways that we're going to be looking at in the next couple of chapters. We're going to be dealing with organic compounds that are made of carbon and other things like glucose. Remember, glucose has 6 carbs in it, C6H12O6. And so it's an organic compound I'm just going to represent with the letter R. And usually there's there's several hydrogen on there, but there's going to be an important hydrogen. I'm drawing that here. So this one hydrogen is bound to the rest of that molecule that probably has a lot of other hydrogen on it too. And let's say it's going to react with some other organic compound. And I'm just going to call it R prime. So, some other one. It's different than R. And when it goes through the reaction here, the hydrogen is going to be taken off of the first one of the hydrogens. And it's going to move to the other compound. And so my point here is, what we just saw right here is not as easy to follow as the formation of an ionic compound. There it's very easy to tell what's oxidized or reduced. So here I'm going to tell you, follow the hydrogen. Wherever the hydrogen goes, the electron is going with it. Now let me repeat that again. Wherever the hydrogen goes, the electron is following with it. So this hydrogen is moving from R to R prime. The electron is going with it. So if the electron is going with it, that means the R is the one that's gaining the electron. That makes this one reduced. And we followed the hydrogen, right? Because wherever the hydrogen goes, that's where the electron is going. Okay? And that makes this one oxidized. So oftentimes we're going to see things oxidized, like glucose. We're going to oxidize glucose. And what are we going to be doing? We're going to be removing hydrogens off of that glucose. In an earlier chapter, chapter 3, I mentioned that there's the energy we're going to be following is often tied in that hydrogen bonds, the carbon-hydrogen bond. So anytime you have a carbon and a hydrogen, there's some important energy associated with those electrons there. Okay, so follow the hydrogens. So in this section, we're going to look at the laws of thermodynamics and to talk about something called free energy. So your first learning outcome is to be able to explain the laws of thermodynamics and then relate a quantity called free energy to the outcome of a chemical reaction, and then contrast the course of a reaction with and without a catalyst. And in biological systems, enzymes are catalysts. So we're going to look at the first law of thermodynamics, and oftentimes it's commonly called the law of conservation energy, which means you cannot create or destroy energy. Okay, so we'll take this mechanical system again with the little girl on the playground slide. We're going to define mechanical energy of this system as the total energy of the potential energy in that system and its kinetic energy. And so there is a mechanical energy when the girl is at the top of the slide in the system, and then there is a mechanical energy there on the bottom. And in both cases, it's the sum of the potential and the kinetic energy. So let's say that as the girl climbs and does the work of climbing, she builds her potential energy. And I'm just going to assign an arbitrary number. with no real units. So I'm just going to say that, let's say we start with something that she has simple like 1,000. She has 1,000 units of energy, whether we measure them in megajoules or whatever. And because she's going to be at rest up at the top of the slide and has no motion, she has 0 units of kinetic energy. And as she goes down the slide, if energy is conserved, then when she gets down to the bottom, she needs to also have 1,000 units of energy. And if she does not, then perhaps we've destroyed energy, and that would be a violation of the first law. So let's take a look here. As she goes from the top of the slide with maximum potential energy, her potential energy is going to be converted to kinetic energy. And if energy is conserved, then we should have 1,000 units of a moving object of her at the bottom. So she reaches her maximum speed down here, would have maximum kinetic energy. But let's say when she gets down to the bottom, we know her potential energy is going to be 0 because she's now not away from the ground, so she has 0 gravitational potential energy. She has 0 units, and that would mean she has to have 1,000 units of kinetic energy. But when you measure her speed, and kinetic energy is related to speed and mass, when you measure it, you figure out that she only has 400 units of kinetic energy, and you're thinking, what the heck happened? We must have destroyed energy. Well, think about what's happening when her body is moving along that slide surface. It's causing friction, and what does friction do? Friction creates a transfer of thermal energy called heat. So heat gets lost to the environment. So here, it's not that we lost because we're short. We seem to be short 600 units. We didn't destroy it. We didn't do that. What happened is that you generated 600 units of useless energy. So it gets released out into the environment as just random useless energy. So what seems like a violation of the first law of thermodynamics is not. So here, during that conversion, unfortunately, we're going to have some energy lost as heat every time. So this is an important part to drive home, is that any conversion of energy in a biological system or in a mechanical system like this one, you're always going to have energy lost to the environment in the form of heat. Okay, so no energy conversion is 100% efficient. Okay, so your second law of thermodynamics has to do with that exact idea, that loss of energy during transfer. And what happens here is that you usually end up with a situation where matter is more highly organized. And the more organized it is, the harder it is to stay that way. There's a tendency for matter to want to become disorganized, which is what thermal energy is. It's just random moving of particles, right? So it turns out that the universe works in a way where the universe is constantly moving towards disorder. And a measure of disorder is called entropy. We're gonna call that S. We've used it S as standard deviation in statistics, but here we're going to call S entropy. So the second law of thermodynamics says that the universe is constantly moving towards an increasing disorder. Okay? A process that increases disorder is more favored, and we would refer to that as spontaneous, right? So any conversions that occur within matter, like chemical reactions, they're always going to be spontaneous or in other words, happen naturally on their own without any extra added input of effort or energy if you're going to increase that disorder. So you go from more order to less order. And I might use an example here. Let's say I put a couple of wooden blocks and stack them up. That's kind of an ordered arrangement, right? That's not favored. Given enough time, something's going to happen, okay? And eventually those blocks fall down. And so now they're more disorganized. So being more disorganized is more favored. So this would be increasing disorder. We could try to go back the other way, but you're going to have to use energy to put the blocks back together again. That's not favored. That's not spontaneous. So increasing disorder, in my picture here, going from stack to less to this more disorder, that's more spontaneous, more favored. So this kind of explains the dirty room example here, the messy room. It's very easy for a room to become messy. That's spontaneous, okay? It just happens, right? And what do we have to do? We have to constantly clean all the time to bring back that order. So if we're going to get that room back and into more shape there, into better, more organized, then that's going to require input of energy. This is not favored. Disorder is favored. Entropy is favored. Here's another example here of increasing entropy. So remember, entropy is a measure of disorder, right? So here we would be increasing because water molecules that are solid and locked in place, that's more ordered. Disorder would be when the water molecules melt, the ice melts and becomes more random moving water molecules in there. So that's favored. We want to bring up the idea now of free energy. We're going to symbolize free energy with the letter G that you see right there. Okay. And free energy is when all of the processes are considered. When you're talking about entropy, when you're talking about the energy and chemical bonds, when all of that is factored in together, how much actual energy is going to be available to actually do any work? And we're going to call that free energy, as in the energy available to do work. And there's going to be a relationship. It's mathematical. And so it's going to see that the free energy, and you can see entropy is in their disorder. A quantity called absolute temperature. It's related to the Celsius scale. Okay. The absolute temperature is actually going to be equal to the temperature in Celsius plus about 273. Okay, so if we were to say 0 degrees Celsius, then that would be 273 Kelvin. Okay, and it's measured in kelvins, not degrees Celsius or degrees Fahrenheit. It's kelvins, and kelvins is the degrees Celsius plus 273. And then you're going to have another quantity called enthalpy. That's the H. Okay, and the relationship there is the enthalpy minus the product of the absolute temperature and the entropy overall. And so again, we want to come back here and remind ourselves that entropy is disorder. And if you're disordered, then there's not much ability to do anything there. So it's unavailable energy. Just like all of the water molecules in the ocean. They're just randomly moving around. There's not much energy in the thermal energy itself. Okay, the real energy comes if we can get that thermal energy and condense it somewhere. In other words, have a higher amount of kinetic energy in one area and lesser in another. Now we can transfer that energy, and that can do work for you here. So this is the actual idea in concept. Okay, and what we want to do is we want to figure out whether or not a process is going to be spontaneous that occurs generally, and also more importantly, these processes occur within your body, within your cells, within your metabolism. These metabolic reactions, biochemical reactions. Okay, they don't violate the laws of physics, and this is a physics equation associated with those changes. This is your free energy, and the delta means change. Okay, anytime you see the word change, and when you have change, that means you have a before and after. So any change in any variable is always going to be equal to the final value minus the initial value. Okay, so when you have delta G, that's free energy, then that means there must be an initial free energy and a final. And so it's always going to be the final free energy minus the initial free energy. Okay, to give you an example here, let's say that we start with particle A and particle B. These could be molecules or atoms, and this is before. And there's a certain amount of free energy associated with these two, okay, particles. And they go through a reaction and they form a product, AB, okay? The AB is going to have a different free energy than the reactants, okay? So you have your reactants, you have your products, okay? So it turns out that before we started, there is, with both A and B combined, this is your initial, they're going to have a certain amount of initial free energy. When the process is done, a change has occurred. That's where the delta comes in. There's going to be a certain amount of free energy, and this is your final free energy, okay? And so there's a difference. Your reactants might have more or they might have less than your products. So these are your reactants. That's initial. And then your products. Or product, right? So product or products. In this case, we'll just generalize products in general. Okay, so your products is always the final, and your reactants are your initial. Okay, so These values can be measured in joules, kilojoules, calories. It's energy, right? Energy units. So let's say that our products here are going to have a higher free energy. Okay, so it's higher, and over here this was lower. Okay, so let's say higher when compared to before, lower when compared to after. Okay, so here, if my initial free energy is lower than my final free energy, and then I go and I think about that equation here, delta G, okay, and I talk about the final minus the initial, okay. Now, if the final is higher in value, maybe it's 1,000, right, and the initial was lower, let's say it's 500, so it's just a lower value. I want you to think about what would the sign of the answer be if you're taking a higher value and you're subtracting a lower value from it. If that's the case, then your answer is going to be positive. Okay, and anytime delta G is positive, okay, that means that your products ended up with higher energy, and that energy had to come from somewhere. It had to come from outside, and that means you have to put in energy. Okay, when you have to put energy into it, it's not spontaneous. It's not going to happen on its own. Okay, this is the case when you're trying to build things like proteins. Energy has to be put in there. Just imagine, like, if we're going to make a building, you have to put energy into making a building. If you're going to build proteins, you got to put energy into it. So usually, when you start making something bigger, it's more ordered, like putting the blocks and stacking them up together. That's going to require energy. Okay. Now, if you want to break down that protein and make something smaller parts, that's less order, more disordered. Okay, situation here. So let's take another example here. I'm going to, instead of A and B, I'm going to use, let's say we start with a reactant CD. Okay, and instead of building up, we break it apart. C plus D. So we start with one particle, and we end up with two. Okay. And again, this is your reactant or reactants, right? And then your product. Okay. And so this is your final, and this is your initial. Now let's say that when we're done, our free energy is lower of the products overall. So that means GF is lower, but your reactants had a higher free energy. So that means, because reactants are always the initial, right, was higher. And we go back to that equation. Delta G is equal to the final free energy, which is the products, minus the initial free energy, which is the reactants. And remember that the products had lower energy. So that's a lower value. And then we're going to subtract from that a higher value, some bigger number. That answer is going to be negative. Okay, and what that means is when you get a negative free energy, that means that this process is, instead of requiring energy, it's going to give off energy. Okay, and negative means losing, so you're giving off energy from that reaction that's going on here. That would be spontaneous. And anytime you got a negative value here and energy is given off, that's referred to as exergonic. You're giving it away, like an exit when you're leaving a room. Okay. We'll go back up to the other one. When delta G is positive, it requires energy input. That's endergonic. Requires energy to go in. Endo means to go in or to be in from there. There are some other points here that I'm going to make by example. Okay, I don't think the book or the original note set gives you a good example, so let's work with an example here. Okay. So keeping in mind, we're going back to this idea of free energy from the earlier page here, where there's a relationship between something called enthalpy and entropy, which we've been talking a lot about. Enthalpy is also important. Okay, remember, enthalpy is going to be another one of those thermodynamic quantities, but this one, it has to do with the chemical bonds. There's energy in those bonds. Remember, it takes energy to break them. When ions form, they give off energy. Okay, so let's take a reaction here. And the text up here is the same as we saw earlier. I just shrank it down and then put it side by side for negative, exergonic, and endergonic. And here we have glucose. And glucose with oxygen is going to react to produce carbon dioxide and water. And for every molecule or mole, it's understood to be one, you're gonna need 6 molecules of oxygen or 6 moles of oxygen, same ratio, 1 mole to 6 moles or 1 molecule to 6 molecules. What that's going to give you is 6 moles of carbon dioxide and 6 moles of water. Okay. Well, it turns out that there's going to be a free energy before and a free energy afterwards. And remember that the free energy, the change in that free energy is equal to the final free energy minus the initial free energy. But there is another equation that shows the relationship there. And anytime you have changes, that means that the bond energies are going to change. There's bond energy associated with glucose, and that's different than the energy of the bonds within carbon dioxide. And same thing for oxygen and water. Okay, so that means there's going to be a change in enthalpy, the bond energy. There's a different bond energies before and after. Remember, we're going to subtract from that the absolute temperature, and there's going to be a change in the order. Are we going from more disorder to less disorder or from less to more? Okay, so in both cases, there's going to be a certain amount of enthalpy and entropy before and afterwards. Okay, and so what I did was I went and I looked up these values, and I found this came from an actual question set for somebody who's probably studying general chemistry, where you cover thermodynamics or thermochem. And here you can see they have values for enthalpy and then entropy values here. And they have them for carbon dioxide. They figured these out. These are accepted values for them. There's for oxygen and for water, which are in this equation. So I went and I looked at these values, and I went and I put them down and just wanted to see how does this all work out, right? So first of all here, when we do all of this, the change in the free energy, the energy before and afterwards, that change in free energy is going to be less than 0, which means negative. And what does this mean? This is exergonic. This process gives off energy, and this makes sense because our cells are going to oxidize glucose and take the energy from there and use it to power the energy needs of the cell. That's why we eat. When we eat, we take in energy nutrients like sugars, right? Okay, so remember that this is going to be your equation here. Okay, this is another way to write the equation. Now, what I want to ask here, just looking at and going back to the analogy of the blocks. When you have your blocks stacked up, that's more order. Okay, if they fall down, they're going to have less order. Okay. Now, you could go back the other way. That's possible, but you're going to have to put in energy. So what I'm going to ask you here is, in our reactants here, the reactants are on the left, the products are on the right. Okay, is the change of entropy. Entropy is how much disorder. Is it going to be positive? And if it's positive, that means you're going to have more disorder. Okay. If it's a negative change, that means you're going to have less disorder. Okay. So this would be positive entropy change. Going back the other way would be a negative entropy change. Okay. In other words, we're asking the question, is there going to be more disorder, which we see here on the right, or less disorder? And I actually ask a question like this. I give you a chemical equation to say, just look at it overall. Does it look like it has more order or less order when you're done? And the way you're going to do that is just look at the number of particles on each side. Okay. This equation is balanced, but on the left you have 7 molecules, or 7 moles altogether, or moles a way of counting, right? On the right, how many particles or moles do you have altogether? 6, 12. So here you have 12 parts. Over here you only have 7. 7 is more ordered, 12 is less ordered. Okay, so what is going on here? Our entropy is increased. We've gone from more order, a bigger molecule, to more smaller molecules, just like the blocks example here. Now keep in mind, if I go the other way, which is actually what the plants use from sunlight, they use sunlight, they use water and carbon dioxide to build sugars. They go the other way, we would be going from disorder to more ordered. That would be an endergonic process, right? So this is what happens when we're burning food. We go to the right. When plants are making food, They're going to the left, and they're using energy from the sun to do that, right? So you should be able to, at a fundamental level, don't get bogged down in the numbers. I'm not going to give you in a lecture or quiz actual calculations to do, okay? But you should understand in concept. More disorder means more favorable type of situation, and be able to recognize when you're getting more disorder. So entropy here, going to the right would be increased, going to the left would be decreased, okay? And if you're increasing entropy, that means you have an entropy, just like a free energy, you're going to have an initial entropy over here, you're going to have a final entropy, and the question is whether or not the change in entropy, just like the change in free energy, when you take the final minus the initial, if it's positive, that means your final had higher value, that means you have more disorder, okay? If you get a negative answer here, that means you had a higher initial disorder and you went to more order. Okay, it's like you're going the other way. So I actually went up and looked up entropy values. I showed you them in that table earlier. And there's units for them in kilojoules. Remember, joule is another way of measuring. And this to the negative one is like saying over moles. So per mole. Kilojoules per mole per degree per Kelvin. Okay, which is like temperature. It's not degree Kelvin, but per Kelvin unit. Okay, I went and I looked them up for all of these values here, and I found them. I showed you that picture of that table, and I wrote them down here. Okay, so these are the values that measure entropy, right? And so right now, the greatest entropy is seen of 0.213 for the carbon dioxide, and for the glucose, it's 0.212. However, this is per mole. There is only 1 mole here, but there's 6 moles here, 6 moles here, and 6 moles here. So that means we have to take these values, because these are the values per mole, and multiply by the number of moles seen in the balanced equation. And when we do that, we've got to take those same values and multiply by those coefficients in the front, times 6, times 6, times 6. You remember, this is initial, and this is final. These are the reactants, these are the products. And we're talking about, we're not looking at delta G right now. We're looking specifically at just entropy, okay? Before and after, there's an entropy associated with it. So when I do those calculations here, 1 times 0.212, 6 times this, you get those values there, okay? And keep in mind that this is right here, that would be the total entropy before. This would be the total entropy afterwards, okay, for this equation here. So when I do that, remember that delta X, delta anything, is the final minus the initial, okay? So on the right side of the arrow is the final, your products, on the left is the initial. And because we have more than one product and more than one reactants there on the left, you have to total them. So it's going to be the total entropy final, which is this final value, minus the total entropy initial. So in other words, I got to take this total right here and put it there, and then I got to take this total, because that's the initial one, and put it right there, okay? And so I went ahead and did that. I substituted the numbers, 1.28 and 0.42 over here and over here, and I asked you to predict earlier, are we going to get more or less disorder? If we get more disorder, it should be positive. And we're predicting that because while we only have 7 units or particles there, over here we have 12 total units, and so this is more disorder, more pieces, right? And when we do the calculations, the numbers become 1.70 and 1.44, and when we subtract them, that's positive right there. There's no negative, it's a positive value. So much like we predicted, you do get a positive entropy, which means more disorder, okay? A negative would be less disorder, okay? So I'm going to go ahead and take those numbers that we just played around with, and I'm going to shrink them down. I'm going to do the same thing with enthalpy. And enthalpy has to do with bond energy. Okay, so remember, there's 2 things, the disorder in the system and the energy in the chemical bonds. It takes energy to break them, and when new ones are formed, the energy is given off when they're being made. Kind of like I'm going to climb a ladder from the ground going up, and then I'm going to jump onto a box that's higher than the ground, okay? I climbed all the way up there, I had a certain potential energy, and then I landed on the box. I actually end up landing on the box higher with higher energy than when I started on the ground, okay? Alternatively, I could climb a ladder, miss the box, and then there's a cliff right next to that box, and I fall down the cliff and fall all the way down to the bottom I'm going to end up with a lot less potential energy than where I was at the very beginning. So the same thing. Sometimes it required energy to climb that ladder. It requires energy to break bonds. The question is, when we make new bonds, just how much energy is going to be given off. So in all cases, the H value, entropy, is always negative because it has to do with the energy when the bonds are being made, and energy is always given off there. Okay, so the question is more energy given off when the original particles were made, or is more energy given off when the new particles are being made? Okay, and so those are, in that case, you compare them. Okay, the idea here now is I went and I looked at the values, and I found out what is the enthalpy for glucose, and it's minus 1273, and these are the units, kilojoules per mole. Oxygen has a value of 0 by its certain standard, and there's more detail to thermodynamics here. For carbon dioxide, to make a molecule of carbon dioxide from carbon and 2 oxygens gives off 394 kilojoules per mole. And then for water, it's 286. And they're all negatives because energy is always given off, right? Now, remember, it's per mole, so we have to take into account how many moles there are, okay? And so it's 1 for glucose, so we put a 1 there, 6 for oxygen, 6 for carbon dioxide, and 6 for that. So when we do that, and I go through all those calculations, I get these values here in this row here, and then we're going to talk about, well, what is the change in enthalpy? Okay, it's always final minus initial, and it's got to be a total because we have on both sides of the equation we have more than one reactant and more than one product. Okay, so I put those totals into this equation, and it turns out that I get a value of negative 2807 kilojoules per mole. Okay. And that's the change in the enthalpy. So when I'm done here, the fact that it's negative means that my products have less energy in them, in their bonds, than we originally started with. If I ended up with a positive value, the bonds would have had greater energy. And in fact, if I were to do the reverse reaction here, I would get the same value, but it would be a positive number, okay? Because the bonds in overall combined with everything there, the bonds would have more energy in them than they did before we started. So whenever you reverse the reaction, you get the same value but the opposite sign. Okay, so in this case, what we end up with is products that have less energy in them, and that makes sense because we're using glucose as an energy source, and when we're done, the products don't have as much energy in them. It's kind of like when you put gas in the car. The gasoline has a lot of energy, potential energy in the bonds, and when you burn it off, there's carbon dioxide that's given off. It doesn't have a lot of energy in it anymore. Okay, so now we do have our values now for this equation. The other form of the equation for free energy, G, is related to the change in the enthalpies, which we just figured out right now, minus the quantity that is the absolute temperature times the change in the entropy, which we figured out earlier, was positive, more disorder. Okay. So if I go and I substitute those numbers, because we just figured out the change in enthalpy, okay, it is minus 2807, okay, and that's kilojoules per mole. And then we have to subtract, so we're going to subtract. And in this case here, the values that I gave you were at a standard temperature. There's these standards that everything else is compared against. And that standard temperature is 298 kelvins, okay, which is about 25 degrees Celsius. And so we're going to multiply that by the change in the entropy, which was a positive 0.26. And that's kilojoules per mole per kelvins. Okay. Now to the negative 1, and this is understood to be 1, whenever you multiply, those actually cancel out, and we get kilojoules per mole, which can add to kilojoules per mole. Now we first have to multiply 26.26 times 298, and I believe that comes out to about 78 kilojoules per mole, and this is 2807. And when you're done, you're going to get, and it's negative. So negative and a negative is going to be, you add them and you still get a negative. And you're going to get 28 like 80, 28, 80, 85 or so, 84. Okay, so this answer right here is your free energy. It is negative. This means that when we started and we consider both the entropy and the enthalpy together to give us our free energy, our initial free energy and our final free energy is lower. Okay, and that means the energy is given off, and that makes it exergonic. It was a negative value overall. And so here, your products are going to have less free energy indicated by the negative than what you started with. Okay. Now, when you're going to get this negative, and by the way, this is going to be spontaneous. It is required. It doesn't mean it's going to happen rapidly, right? But it just means it's going to naturally happen. No energy input is needed. When does this happen? They give you some keys here. Whenever the change in the enthalpy is lower, and it went negative here, and we should say lower from before the reaction to afterwards. That's another way of saying the change was negative because the product is lower. Okay, and if the entropy, which means you get more disorder, is higher, but really that means from before you started, you had a certain entropy, and afterwards you have more entropy, more disorder. That's really saying positive change. And that's what we got here. This was positive. There was no negative. It was a positive change there. Okay, now think about this. If we were to go the other way, the signs would be opposite. You would get the same values because energy is conserved, right? It's the same energies, but you're going the other way. That means if we were going to the left and we're trying to build sugar like the way plants do in photosynthesis, then this would be negative 0.26, negative 0.26, and this would be positive 2885. Okay, and let's see here. That would end up being endergonic. We're going to end up getting a positive G value overall. You're going to get the opposite sign. And let's think about what happens here. Is the change in enthalpy not higher, comparing before to after? Is it positive? It would be positive if we were to reverse it the other way. And is there less disorder, right? In other words, the change in entropy is lower. In other words, you're going to have a negative change, which means you're going to have less disorder. And that would be the case if we reversed it. And that would require energy input, and it would be endergonic overall. So I'm not going to ask you to do a thermodynamic problem or calculations, just trying to demonstrate that if you went through the mechanics of doing this calculations, you get these answers, and that makes these statements make more sense. The only reason I went through a calculation to show what the value is there was to show you what these statements mean. You got to understand what they mean so you can answer questions in concept, not be able to do math calculations. Okay. So here's another way to think about it. These are the current images in the new textbook. They changed them from the older one. I like the older one better because this line kind of shows us that a change is occurring as we go from reactants to products. When it says course of reaction here, this means time. Okay. And this is free energy here. Okay. So when you think about it here, we're starting over here and we're ending over here. So initial on the left with your reactants and then your products over here. Okay, so with your reactants, when we're starting over here, that makes this, because the y-axis is free energy, that makes this your initial free energy, and then up here, this is your final free energy. And our final free energy is bigger than our initial free energy. Remember that the change in free energy is, any change is always final minus initial, always in that order. Okay. Now here, our final energy is higher, and our initial energy is lower. And when we do the subtraction here, you're going to end up getting a positive answer. And positive means greater than. This makes this, you have to put energy in to get up that hill there. That makes this not spontaneous. This would require energy input. Okay. Now, over here, we have an exergonic situation. This is our initial energy because we're starting here at time 0, and then when we're done, as time progresses and the reaction happens in, split seconds there, this would be your initial energy, this would be your final free energy, and your change in energy is going to be equal to your final minus your initial. And our final energy is actually lower than our initial one. So this is lower, this one is higher, and when you end up subtracting those two, you're going to end up getting a negative value. That means your free energy is less than 0, This is exergonic, energy is released. This one would be spontaneous. They're showing the same thing here, but they're showing it with bar graphs overall. So now the idea of activation energy. Okay, so we come back over here and say, well, if we use a physical analogy, now to put a rock up here, if that rock is at rest, it would naturally want to come downhill. It would do that all on its own, except it's at rest up there. And oftentimes, you need to give it a little push to get it to go. Okay, it's the same thing with chemical reactions. You can't just get a reaction to happen. You have to put energy in there to break the chemical bonds in the reactants. You have to break bonds in order to make new ones, right? So energy is always required. So just like we need to provide energy in the physical analogy of a rock up on a hill, okay, and there's the hill right there. If there's a bump right there, it's going to be even harder to get it started. But once you get that rock over that little bump, it's going to take off on you. And it would be totally spontaneous. Okay. So that's what we're talking about here. This activation energy. This is the energy that's going to be required to destabilize the old bonds, the existing bonds, to start that chemical reaction. Okay. So even an exergonic reaction, the one that goes downhill, like this one right here, that's spontaneous, requires activation energy. For a endergonic, a lot of times you have to put in a lot more energy. It's not spontaneous, but you have to even get it over a little hill to get the final products there at the end. So you have to put even a little bit more energy to get that final product there at the end. Okay, so, but even for these downhill reactions, you're going to have to get it over a bump, and that bump is the bonds that need to be destabilized, the original bonds, right? Now, if you have a larger activation energy, you're going to have a slower process. Even if it's spontaneous, it's going to take more time to occur there. Now, we can increase rates in different ways. And one of those ways to increase the speed that a reaction will happen. So again, just because something's spontaneous doesn't mean it's going to happen right away, okay? But you can increase the rate of a spontaneous reaction by heating it. And what do you do when you're heating it? You're transferring thermal energy in there. You're speeding up the particles. They're going to collide with each other more, and you're going to get more reactions occur. The other one would be to lower the activation energy. Okay. So going back to that graph earlier, let's say we started with, and we're dealing with an exergonic reaction, and your reactants are up here. Okay. And then your products end up down here somewhere with this energy here. This is your free energy. Okay. And you actually have to put energy in, and then eventually you get to your products over here as time progresses. Okay, you got to get over this energy bump right there. Okay. This energy bump right there, that's going to be your activation energy. Okay. Now, sometimes the active energy, it takes a lot more energy to break the old bonds and destabilize them. Sometimes it takes less. Okay, but if you could do something to lower that activation energy, then your reaction is going to happen faster. And one way to do that is heat the system. Another way is to lower the activation energy. Okay, so let me go back again. You either heat the system or you lower the activation energy. Okay, so you heat the system, more collisions, you're going to have more molecules making it over that tall hill. Or if you do something to lower the activation energy. Now notice, whether I heat the system or I lower the activation energy, lower that bump, we're still starting at the same place. Okay? And we're still going to end at the same place. So the change in G stays the same. We're going to, because as you go up that hill, you have to put in energy, but you're putting in energy, you give off that energy, the same amount of energy when you get right back to that point. So the real action of any real change that's going to happen, net change, is going to start at this first horizontal line. Okay, so whether you have a high activation energy or you lower it, you're going to have the same delta G regardless. And that's important because you cannot have a different free energy. You'd be violating conservation of energy. You'd be violating laws of thermodynamics. Okay. So how do we lower activation energy? And there's going to be something called a catalyst. Okay. So catalysts do this. They assist the reaction. They don't become part of the reaction, right?
Where does the energy for chemical reactions come from? Many chemical reactions, even exergonic reactions, require an input of energy to get started. On ancient Earth, before the formation of macromolecules, chemical reactions were powered by lightning, sunlight, and heat from molten rock. On the modern Earth, living organisms, including humans, most often obtain the energy they need from other molecules. Cells use the energy in these food molecules to power chemical reactions. However, the energy cannot be used directly. It must be transferred first to an energy-carrying intermediary, such as the compound adenosine triphosphate, or ATP. When chemical bonds in ATP are broken, energy is released. This process provides the energy needed for chemical reactions which power life. This graph shows a hypothetical reaction between atom A and a molecule containing atoms B and C. The activation energy, EA, is the amount of energy needed to get the reactants to the transition state in which bonds are broken and new bonds are formed. This transition state usually lasts for a fraction of a second. In this example, the products of the reaction are the molecule AB and the atom C. Because this is an exergonic reaction, some of the energy stored in the reacting molecules is released. Often, activation energy can be a barrier that prevents a chemical reaction from occurring, except very slowly. The activation energy for many chemical reactions can be reduced with catalysts. Without catalysts, many of the chemical reactions of metabolism would occur too slowly to support life. Catalysts stabilize the reactants in the transition state, allowing old bonds to break and new bonds to form. Even though the activation energy is lowered by a catalyst, the amount of energy released by the reaction is unchanged.
So here's what we're talking about here. So again, you can either speed up or lower the activation energy. So let's say this is the original activation energy. This is the energy we have to put in to destabilize, and then we've broken apart the original bonds, and now the new bonds start to form. And new bond formation always gives off energy. So we start to come back down, and we get back down to that original line. So there's been no net change in energy at this point. Anything after that now is a net change in energy. So the delta G, this is our initial energy, our final energy down here. Okay. Now, if we lower our activation energy, and in red here, it's due to a catalyst. Okay, that's going to help us speed up our reaction. Okay. So this brings up that definition of catalyst. These are going to be substances that influence chemical bonds in a way that lowers their activation energy. I mentioned you cannot violate the laws of thermodynamics. That means it's not going to give you a different delta G. You still get the same change in free energy. You're just lowering that little bump where you have to invest some energy to get some back. Okay. So it's not going to change delta G. You can't make delta G positive if it was negative, or vice versa. So it's not only is it it's not going to change delta G anyway in any way, not making the change in free energy more or less, and it's not going to make a positive negative. So you can't make an endergonic reaction spontaneous with an enzyme. Okay, so that would still require energy input, and it doesn't. It's not going to alter the amount of reactants in products either. So same graph, and it's showing the activation energy without a catalyst, and then the activation energy with the catalyst. You can see delta G is still the same, because after we invest that energy, whether you have a catalyst or not, you're going to have that energy given back off, and you end up back at where you started. Net change is zero. The change happens after that dotted line. Okay. And that change is the same whether you have or you do not have a catalyst. Okay. So in this section, we're going to look at ATP, adenosine triphosphate, as the primary energy currency. What's used to do all of the biological work within the cells. So your learning objectives here are to describe the role of ATP as a short-term energy storage, and then distinguish which bonds in ATP are the high energy ones. ATP does stand for adenosine triphosphate. It's something we covered when we were looking at nucleotides that make up DNA and RNA. It is basically a nucleotide not with one phosphate but with three phosphate groups. And it has the nitrogenous base called adenine. It has your 5-carbon sugar called ribose, and then 1, 2, 3 phosphate groups. Now the real energy there is in the high energy bonds between the phosphates. So when you break off one phosphate, it can give off energy, and that energy that's given off, it's exergonic, can be used to drive endergonic processes. So our processes are going to be coupled. We're often building biomolecules, and anytime you build up something, it's always going to require energy to build. You break down other things, you oxidize other molecules, that gives off energy. Okay, so this is just a description of and a review really of what ATP was. Ribose, your sugar, adenine, and then your phosphates. If you break off one of them, then you have ADP, which stands for diphosphate, and if you break off a second phosphate, then you have monophosphate, adenosine monophosphate, which is the lowest energy form. So the most energy is when you have ATP. ADP has lower energy, and then AMP the least amount. Okay, so that's just a picture of the molecule again. Now, remember when we break things apart, usually you have to put water in there to split. It's called hydrolysis. And the hydrolysis of ATP actually has, this is a net negative G. That means that the change in free energy when you break off a phosphate by hydrolysis is going to be negative. Okay. Not only is it negative, off the top of my head, it's somewhere around negative 7 point, I think it's 0.3, something like that, 7.3 kilojoules per mole of ATP. So it's exergonic. It gives off energy. It's spontaneous. That energy given off can be used to power other processes that are endergonic and require energy. Now, ATP is not very stable, so it's not suitable for long-term storage. So the phosphate bonds are actually unstable, and so fats and carbohydrates are actually a better way to store energy, and the energy is stored in the carbon-hydrogen bonds. And remember, when we remove those hydrogens, we're basically oxidizing the organic compound and then moving those hydrogens to others, right? So your cells are actually only capable of storing a few seconds worth of ATP. And so we constantly have to oxidize carbohydrates as a quick energy source. You run out of those and you start going into fats. And you break those down so that you can help regenerate ATP. So essentially this is how it works. You take, let's say you have ATP, and there's energy in that, in the phosphate bonds there. And you're going to go through hydrolysis. You would bring in a water molecule in there to break it off, and you're going to end up with adenosine diphosphate. And the phosphate that broke off is no longer bound to the organic molecule, the adenosine, and so you have your inorganic phosphate. So the PI stands for inorganic phosphate. Now, the ADP is not used to drive energy, but we can recycle the ADP back to ATP. So this process right here is going to give off energy. Okay. If we're going to go back the other way, we need to put energy in to get back ATP. Okay. So where are we going to get that energy to build ATP from adenosine triphosphate? We're going to get it from our energy nutrients, carbs, and fats. So this is the basic idea of what I just drew for you earlier. Now, if we're going to take our adenosine diphosphate, is what we get when we use ATP, use up ATP, and our inorganic phosphate, and we're going to add those together, okay? And we're going to need energy, and we're going to get the energy from the exergonic cellular reactions, which basically is the oxidation of food, of your organic molecules. When we oxidize, we're going to break down sugars and so on, so that energy is going to be used to help recombine these to make ATP. And when you do, you're making a bigger water molecule. Remember that water is given off, okay? Dehydration synthesis. Okay? Now, if we are going to use that ATP that we've generated, it's going to break apart here. When we use that breaking apart the ATP, you're breaking off the phosphate, hydrolysis of ATP gives us energy. It's It's an exorganic process that can be used, that energy that's given off can be used to drive endergonic processes. Okay, so the endergonic processes are the processes that the work we're doing in the cell. We use ATP to do that. Okay, so the energy given off by ATP, this is energy being given off. We're giving it off. What's it going to be used for? It's going to be used to drive those endergonic processes. Here, we got to put in energy, and that energy is coming from the oxidation. So in this section, we're going to look at biological catalysts, and they're called enzymes. And so your learning outcomes here are to discuss the specificity of enzymes. And this has to do with how they're specific for the specific substrates, they call them, that they act on. And then your second objective is to explain how enzymes bind to their substrates, which is what they help the reactants that they help go through reactions. And then number 3, you're going to list the factors that influence the rate of enzyme reactions. How fast enzymes are going to speed up reactions because they're catalysts and they're going to lower that activation energy. Remember that even in an exergonic reaction, we have to get over that little energy bump, the activation energy they call it, right? So that little energy bump right there is that activation energy. And so the enzymes technically are going to be proteins. These are special globular proteins. And there are some RNA molecules that also serve as catalysts, but they're going to be called ribozymes. We'll mention those there in a little bit. For the most part, when we say enzyme, we're referring to protein molecules that help serve as catalysts. Now, the shape of the globular proteins are going to have a specific shape. They're going to be very specific for the reactants that they assist going through a reaction. Those reactants are called substrates. Okay, the enzyme itself is not going to become part of the reaction. Its only involvement is to help by binding to the substrates and assisting them by lowering their activation energy. And an example here is one called carbonic anhydrase, and I want you to notice that ending there, ASE. Anytime you see ASE in the context of our biochemistry reactions, ASE is how they name enzymes. So amylase, alcohol dehydrogenase, sucrase, lactase, acetylcholinesterase, all of these enzymes, and they name it ends in ASE. Now, they don't always do that, but anytime you see ASE, you can probably assume it's an enzyme. So in this case, this specific example of carbonic anhydrase, it's an enzyme that helps when carbon dioxide is generated in your tissues. We want to convert that to a form that's more easily transported. So it's going to be converted by reacting with water to bicarbonate ion, which is HCO3 with a -1 charge. So sometimes they call that carbonic acid. It's a weak acid. So your carbon from your carbon dioxide is right in there, and that's how we transport it. And then it'll go to your lungs, and then it gets converted back to carbon dioxide. Without the enzyme, only about 200 molecules of carbonic acid per hour can be made without the enzyme. But when you have the enzyme in there, and this is per hour, you can make 600,000 of those reactions occur per second. That is an amazing jump in the speed at which you can cause the reaction to occur. And so the reaction might not normally occur at any significant rate. Put an enzyme in there and boom, you've got a good reaction going. So this is our general model here. This is just a space filling model. And those spheres represent the parts, the amino acids that build this globular protein. It's dissolved within the environment. And enzymes are going to have a specific location on there that is very specific for a substrate. So whatever the substrate is, this enzyme has been built by coding your genes to be very specific for that substrate. So the substrate is recognized by this active site. There is just an affinity for whatever that substrate is, and when it comes in and it binds, the enzyme itself changes shape, and that's going to create strain on that substrate. Remember, the molecules that were the substrate is going to be a molecule, and there's chemical bonds in there, and if you can create stresses on those bonds, you can lower that activation energy because you're partly helping to break those bonds, the initial bonds there. So here's going to be your basic model here. The active site is that part that the substrate binds to. It's like a pocket within the globular protein. We saw that earlier. When the enzyme bound is bonded to the substrate, it's called the enzyme substrate complex, or ES for short, complex. And it's very specific for that substrate. Now that bonding is going to create a stress in the bonding, and that's going to help you lower your activation energy. And the model is an induced fit model, because when the binding occurs, the enzyme actually fits even better. The enzyme changes shape a bit and fits even better, and then creates that stress. Here is a model of the process over here. This is an enzyme called sucrase. There's that ending, ASE. And sucrase has an active site. It's a very, very simple diagram here showing this. And this is your sucrose molecule. Sucrase acts on sucrose. Sucrose is that disaccharide we covered back in chapter 3. It's made up of a glucose and a fructose molecule, and they're bonded right there by a special covalent bond called a glycosidic bond. And in order to break that bond, we're going to have to split it with water, hydrolysis. Now, this reaction might happen on its own at a slow pace, but if we put an enzyme in there, we can have it happen more rapidly. So with the enzyme present and your substrate, in this case sucrose present, we bind, we induce the fit there, and that creates the stress in that bond there. Water is present everywhere, so water gets involved in the reaction, not the enzyme. The enzyme does not become part of the reaction, it's just assisting. So that water is put in there and used to help split into glucose and fructose. So this is your product. Before it was the product, we call the reactant, we call it a substrate. So this is your substrate right here. Your substrate binds with the enzyme, forming your enzyme substrate complex. And that's going to create that stress in the bond. And then with the help of water, we split. So water is actually the other part of the reactant there. Once the products are produced, the fit no longer applies because it's not sucrose anymore, and the product is released, and the enzyme didn't become part of that chemical reaction. It assisted. That enzyme is now free to repeat and act on another sucrose molecule. So be familiar with this overall process. You can use sucrose as an example, or just more generalized, just call it a substrate, and then products are produced. So as I recommend with students all the time, you should be able to describe this process with both a sketch, basic labeling, and be able to write about it. And keywords in there would be substrate, enzyme, active site, would all be terms that you would use, because these are labels that talk about the structure. There's a structure here, and then there's a process that's occurring within this structure. This is just part of a structure that's happening within, say, your body, right? And so those key terms would have to come out when you're trying to explain this, and they would include substrate, enzyme, the enzyme substrate complex with an N, and of course your product. And a key part in there, the enzyme also has active site. That might be another term I might use. And then a key thing that happens during this enzyme substrate complex, what happens? Lowers activation energy. So as I'm brainstorming on what I might sketch, what are things I might label? Enzyme substrate would be labeled enzyme substrate. Product would be labeled. Active site could be labeled like it is right here. Lowering active energy, that's a concept that would come out. It's not necessarily a label in here. And all of these would be key terms that would come about in an explanation of it, right? So if you can sketch, brainstorm the key terms that are part of your sketch and some names that are associated with the processes, now you can write about it in your own words using key terms. And that would be how you would go about doing that final stage of study called self-assessing, recreating information, right? So that's just a picture bigger. Now, there are different ways in which enzymes can be structured within cells or within your body or the body of an organism, whether it's a single-celled organism or multicellular organism.
Enzymes are proteins that speed up chemical reactions in the cell. A special region on the enzyme, called the active site, has a shape that fits with specific substrate molecules. An enzyme works by binding to one or more specific molecules called reactants or substrates. Binding occurs at the active site. The enzyme and substrates form an enzyme-substrate complex. The interactions between the substrates and the enzyme stresses or weakens some of the chemical bonds in the substrates. These stresses encourage a link between the two substrates, leading to the formation of a different molecule. As a result of the chemical interactions within the active site, a new product is formed. The product is released from the active site. The enzyme assumes its original shape and is free to work again. Although this reaction has specifically illustrated the formation of a single product from two substrate molecules, other enzymes catalyze the formation of two products from a single substrate.
In some cases, enzymes may be suspended within a cell membrane, so within the cell itself, and that provides a more ordered structure. If they're suspended within the membrane, then the reactions can occur right near the membrane. Sometimes you have enzyme complexes. So you have several enzymes together, and those may be embedded within a membrane, or they may be free in a cytoplasm. And they have one here as an example. This is called pyruvate dehydrogenase. There's that ASE again. This is an electron micrograph of that specific enzyme, and you can see it has several active sites on there. It's made up of 60 different protein subunits. Those are just little details that are, wow, that's cool. Don't memorize that stuff, right? But the point here is that if a reaction occurs here, the products are released and they're right nearby the next active site. So this gives control. We don't want our product going somewhere else and becoming involved in a side reaction, because sometimes the products are used in different types of processes, different types of metabolisms. And if you want to really make sure you're going to make something, then you're going to want the next enzyme right by you. So why not have it in the form of a complex, right? Here. So what this does, it prevents unwanted side reactions, so you don't waste each step. There's going to be a product, right? And so they would be called intermediates, biochemical intermediates. All along the way, you got to change it one step at a time, and so on. In our next chapter, we're going to look at how we make ATP, and one of the first metabolic processes is the splitting of glucose, and that occurs in 11 steps, requiring an enzyme for each step. And each part of that process, there's an intermediate, and you want it to make sure it goes to the next part of the reaction. And then there's the ribozymes, which I mentioned earlier. These were described in 1981. There was no real image in the textbook, so I went ahead and just found one just so we can visualize it here. But it turns out RNA can also reduce activation energy for certain reactions, and there's two general ways that this might come about. The RNA molecule actually causes a change on itself. That would be intra. Intra means within. So this would be an intramolecular catalysis, or catalyzing, right? And so here you catalyze a reaction on your own molecule, on yourself. The other one is intermolecular, and this is where RNA acts on another molecule and causes a change on that one, lowering its activation energy. So I just found an illustration of one. Here's one called a hammerhead ribozyme. It's actually made of RNA itself. This is a single strand of RNA. It just seems to be looped upon itself right here. And these right here, those are the base ends. Remember, RNA is made of nucleotides, and there's nitrogenous base. These are your nitrogenous bases right here. And the nitrogenous bases follow pairing rules. So let's say this is acting as your enzyme. It's a ribozyme. And here it's basically got a sequence that matches the sequence on some other RNA, in this case a messenger RNA. And so it'll bind very specific to that sequence there. And when it does bind, it causes a reaction. In this case, the reaction is going to cause a lysine, or a splitting, or cleaving, means to split, of that RNA. And there's your ribozyme. It's free to go and attach again, kind of like a protein enzyme. Okay. Now, when it comes to enzymes and how fast they can cause a reaction to occur, there is a range in which the enzymes work most efficient. Okay, and because they're globular, that means they're dissolved within their environment, they are heavily influenced by the conditions of that environment. If we can take factors like temperature, pH, ion concentration is another one. all of these factors can change the shape of that globular protein, which is serving as an enzyme. And there is a specific conformation or shape for that globular enzyme that has to be there for the active site to work correctly. And what happens if you change a factor like temperature or pH too much within the environment where that enzyme is, that enzyme starts to change shape and then won't function correctly. Okay, and it can get to the point where it doesn't function at all, and that would be called denaturing. So if you denature a protein, in this case you denature an enzyme, you're going to mess up the reactions. They won't happen because your enzyme no longer functions. So it turns out there is a range in which the enzyme works best. Okay, so I'm going to take an example here. It's not necessarily in your book, not illustrated, but I want to illustrate it so it's kind of understood here. Let's take temperature. Okay, so let's say we test the temperature on an enzyme and you need a way to measure what the enzyme is doing. And so the enzymes cause a reaction to occur, so you might be able to measure a product in some way. So let's say there is an enzyme like one called catalase, which can break down hydrogen peroxide. And hydrogen peroxide actually is produced as part of your metabolism. It's very toxic. So an enzyme called catalase, for example, catalase, actually will break the hydrogen peroxide into water and oxygen, which is much less harmful than H2O2. H2O2 is not water, it is hydrogen peroxide. So it can break that down for you there, and I didn't balance it, but overall it generates water and oxygen. Now oxygen is a gas, so in the lab, if we play around with catalase, we can measure the amount of bubbles that are produced. So little bubbles are produced. So in other words, you can measure how much gas is produced overall. And so let's say that we play around with catalase and we want to vary temperature. So we take different test tubes, put the hydrogen peroxide in there, and then introduce catalase, and then see how fast does that catalase convert and produce oxygen gas, right? So you measure how much gas in this case. There's different ways, depends on the enzyme and the product, how you might measure the enzyme's activity. But let's say that we start at, say, 10 degrees Celsius, or even near freezing, 0 degrees Celsius. And your product, in this case, the product here, how much is produced? Let's say it's the oxygen gas. I'm just going to write product in general. And over time, you're going to get more and more product. So we get a line that looks like this. So let's say that this is at, let's say that's at 20 degrees Celsius. Okay, and then we put another test tube in there and we do the same reaction, and we do it at a warmer temperature. And let's say this is at 35 degrees Celsius. And the fact that the slope is higher, this means we produced more product in that same amount of time. It was faster. Okay, we continue to increase the temperature. Let's say we go to 45 degrees Celsius. Okay. And then we go up to, I don't know if these are actual temperatures for 50 degrees Celsius. And then we go and we try something like 60 degrees Celsius. And all of a sudden, at 60 degrees Celsius, this is just a hypothetical enzyme, maybe one that produces a gas as well. And you can see now that the rate has been affected negatively. Now at too high a temperature, all of a sudden the enzyme wasn't working that great. Okay, so what do we have here? We have here a amount of product versus time graph. And it turns out that if we calculate the slope, remember the slope in algebra, this should be a straight line here, was m, and it's the amount of rise over run, right? And that slope in this case of this graph would be the amount of product per unit of time, say per second or whatever. Like miles per hour, that sounds like a speed, right? And a speed is a rate. So these are rates. So the slope of these graphs here at each of the different temperatures gives us the rate. And if we take those rates for each of these, the rate at 60 degrees, 20 degrees, 35, and so on, we get what's called a derivative plot. A derivative is in calculus is the slope. Okay, and we just and you know how to calculate the slope from algebra. When the line is straight, you can calculate the slope very easily. And let's say we go and we plot the slopes. Those slopes would be the rates. So here, if we plot the slope against the temperature, okay, we're going to find that at 20 degrees, let's say this was the 20 and you got your different temperatures going this way. Okay, I'm not going to go and scale the axis, but what will we expect here? Well, at 20, we have some rate here. At 35, it was higher. At 45, the speed was higher. And then at 50, still higher. And then we got to 60 like this. And so now if we draw a roughly smooth line to represent that pattern there, we get an activity plot or derivative plot that shows the activity across different temperatures. And you can see that right up in this area here, we have the optimum speed at which that enzyme occurs at. Once you start getting too low a temperature or too high a temperature, the enzyme doesn't work as well. And one of the reasons when you get too high a temperature is that the shape of that enzyme changes so much that the active sites no longer work. It's no longer able to bind to the substrate because you're beginning to denature that protein. Okay, so this is what we're talking about. We're talking about optimum temperature. We could do the same experiment, but instead of different temperatures like we did here, we do it for different pHs or different ion concentrations. And now that makes this graphs make more sense. These graphs are the slopes of the first graph I drew, the rates at different temperatures here. Okay, so here is it's like a human enzyme, and its optimum temperature, the temperature at which it works the best, is around 40, 41 degrees. Human body temperature is about 36 degrees Celsius on average. It can swing between normal limits. Once you go too high or too low, though, death can occur, right? So you keep your body temperature within certain limits. So it makes sense that a human enzyme, one that's found in our body, is optimum around our body temperature, right? But what about an enzyme for a bacterium, a prokaryote, that lives in a very hot environment, a hot spring, where the temperatures are pretty high? Let's say when you start getting to 70s and 80s, you're getting near those temperatures where water's going to start boiling. Water boils at 100 degrees Celsius. So this kind of temperature here would feel very uncomfortable, if not scalding. It would start to cause redness in your skin and so on. But this bacteria is quite at home. And it turns out that this one's optimum temperature is there. And if you get too low, the enzyme doesn't work very well. Too high, you denature. The same idea with pH here. If we talk about an enzyme called pepsin, this is a case where these enzymes don't follow the ASE convention. Pepsin is an enzyme, right? And so its optimum pH is over here in quite acidic conditions here. And why? Well, pepsin is found in your stomach where the pH is low. There's literally hydrochloric acid in your stomach. And pepsin begins to digest protein. So protein digestion starts in your stomach. And then when that food, partially digested food, gets into your small intestine, your pancreas secretes neutralizing substances that help neutralize that the acid and brings the pH up. And in there, another enzyme is present called trypsin that continues to help break down protein. But trypsin's optimum pH is much higher, closer to neutral. And so trypsin will not work at a lower pH, and pepsin will not work at a higher pH. They have optimum pHs at which they act based on the environment that they're in, right? So, and the same idea here, this axis is the rate at which that enzyme is working under varying pH conditions. So enzymes also have the possibility of becoming inhibited. An inhibitor is going to be a substance that prevents the enzyme from working at all. Okay, so there's different kinds of inhibitors. So what is an inhibitor for an enzyme? An inhibitor is going to be a substance that is going to bind to your enzyme, and that's going to lower the activity because it's going to interfere with the enzyme working. Anytime something binds to a globular protein, it changes its shape. Okay, there could be, and there's two categories. There's competitive inhibitors and non-competitive inhibitors. So for the competitive inhibitor, the inhibitor is actually binding in the active site. The enzyme itself actually can bind on occasion to some other item, perhaps by design, that gets in the way of the active site. So here's your normal substrate here, and it cannot bind in there for the enzyme to do its work. And so this is a competitive inhibitor, and if it's bound in there, then your substrate cannot come in there, and then we cannot cause the reaction to occur. Okay. For a non-competitive inhibitor, this would be another kind of molecule that binds to some other location on the enzyme. And when it binds to that other location on that enzyme, it causes the shape change. And here is your non-competitive inhibitor. And it binds to another location. When it does, it causes a shape change in the active site, and the substrate still cannot bind. That's non-competitive. Okay? And some enzymes are built this way with an inhibitor on purpose, and that gives control over these enzymes. Okay, so that would be the case of non-competitive. So in this case, your enzyme itself actually has two shapes. Okay? So when your enzyme can have two forms, two conformations, it's called allosteric. And that's going to be covered on the next slide here, but that's why you see allosteric site. The location is other than the active site here. And your inhibitor would be an allosteric inhibitor. Okay, so this is just the same images here. This one's showing competitive, a competitive inhibitor, and this is a non-competitive inhibitor. It's often some sort of allosteric binding to an allosteric site, which changes the conformation of the protein. So when it comes to allosteric enzymes, remember allosteric means you're going to have two forms, two conformations. One is going to be active and the other is inactive. And it depends on the molecule being bonded to it. Sometimes when an enzyme is built by the ribosome, the enzyme itself is its shape is inactive. It's in an inactive form. And in which case you have to activate it with an activator instead of an inhibitor. In other cases, the enzyme is programmed and built to already be active, and then the molecule that binds to it is called an allosteric inhibitor and binds to it and causes it not to work. The example that was given earlier is an allosteric inhibitor. But imagine a case where an enzyme is built in a way in which the active site cannot bind to the substrate. That's its more normal way, and it needs to be bound to another molecule in order to activate it. Okay, so that's kind of the opposite of what you see here. So there's basically two kinds of allosteric enzymes, and the kind depends on what the enzyme is. There is enzymes in which they are normally in a switched on sort of condition. And in which case, if we're going to control them, then we need an allosteric inhibitor. So the allosteric inhibitor would bind to it and cause the shape to change so that the enzyme does not work. Now, if you have an enzyme that is normally in a switched off position, right, like or a conformation where it's not going to bind to the substrate, and you want it to activate it or switch it on, right, then you would need an allosteric activator to bind to it to change its shape so that it becomes active. Okay, so this way of controlling those enzymes. This section is on metabolism, and metabolism is basically a description of all the chemical reactions that occur within your cells or within the body of the organism. Here your learning objectives are to explain the kinds of reactions that make up a metabolism, and then discuss what is meant by a metabolic pathway, and then to recognize that metabolism is been shaped by evolutionary processes. So what is metabolism? It is the total of all your chemical reactions carried on the body, and some are going to be building up and require energy. Those that build up are called anabolic reactions or anabolic metabolism or anabolism. And what's meant by expending energy means you have to put energy into this process. Then that means it's an endergonic process. Okay. The endergonic processes are going to be driven by catabolic processes. These are processes that break down, or catabolism. And breaking down is usually to harvest or get energy when you're breaking down. And so these catabolic reactions are exergonic, like when we're oxidizing food to make ATP. So during our metabolism, we're going to have biochemicals, sometimes referred to as metabolic pathways. And sometimes you'll hear me use the word metabolic during explanations. And here there's going to be a sequence of reactions where The reactants go through a change, they become a product, and then that product now is a reactant in the next part of the process. And so this occurs in a sequence. These processes may occur in different parts of the cell. So here we have a situation where you have enzymes right here, enzymes 1, 2, 3, and 4 within your biological membrane, could be the plasma membrane. And enzyme 1 is going to work on your initial substrate in this hypothetical example. And they're drawing them different shapes just to, in diagrams, show that it's a certain kind of molecule that goes through a change. So here it binds with the, in the active site here, goes through its change, and then is released as a product. But that product now is going to go through another change and requires another enzyme. Okay, so the next enzyme, the product is going to be referred to as an intermediate. It's not your final end product. And so now this binds with enzyme 2, and then it goes through a change, and now it's your second intermediate, and then goes through another change and forms another initial. So all of these then, right here would be chemical intermediates or metabolic intermediates. And then finally here in your last enzyme goes through its final change for your final product there. So this is just a very simple, simplified metabolic pathway in which enzymes are embedded within a plasma membrane. The enzymes, of course, could be free, or they could form multi-enzyme complexes like mentioned in an earlier section.
Organisms contain many different kinds of enzymes that catalyze a variety of different reactions. Many of these reactions, such as those involved in the biosynthesis of an amino acid, are carried out in a specific sequence called a biochemical pathway. In such pathways, a substrate is converted into a product by the first enzyme in the pathway, and the product of the first reaction then becomes the substrate for the next reaction. The product of the first reaction then becomes the substrate for the second enzyme. The sequence of reactions continues until the final product is made. When a biochemical pathway is functioning, the initial substrate is continually converted to the final product through the series of steps in the pathway.
During these metabolic or biochemical pathways, as this pathway is, which is being facilitated by the help of these enzymes, as the pathway is operating, after a while your end product is going to build up in concentration. So your end product increases in its concentration, and at some point you're going to want to stop that process. And one way to stop that process is by way of feedback inhibition. And so like any system, and this would be a subsystem within, say, a cell, any system is going to have inputs. And the input could be materials, like these substrates. It could be energy or information. And so that input goes in there, and then within that system changes occur, and then there's output. And that output could be materials, matter, energy, or other information. And so in this case, the output of a metabolic pathway is your end product. And that output actually provides feedback on the system. And this is true of any system, even man-made systems. That feedback goes back and informs the system as to whether or not to continue in the direction that it was going. So that's called feedback inhibition. And if the feedback causes a slowing down of the process, then it would be called negative feedback. So what's happening here is, if in this case, if your end product is also an allosteric inhibitor, something we mentioned in the prior section, and that is that as you start building up the concentration of your end product, eventually there's so much of this molecule around, it starts to bind with an allosteric site on the enzyme, not the active site, but an allosteric site. And when it goes and it binds, it changes the shape of your enzyme, and the initial substrate can no longer bind. And what you've done is you've stopped that metabolic pathway. And that only happens if your end product has built up in concentration. Okay, so in this case, the output provides that feedback to stop the process, and in this case would be because the product, your final product, ends up serving as an allosteric inhibitor.
Many of the enzyme-catalyzed reactions that occur in a cell, such as those involved in the biosynthesis of an amino acid, are carried out in a specific sequence called a biochemical pathway. In such pathways, the product of one reaction becomes the substrate for the next reaction. If the end product of a pathway, such as an amino acid, becomes available in the environment, it is unnecessary and wasteful for the cells to continue to produce the product. Cells therefore have the ability to shut down a pathway when it is not needed. In feedback inhibition, the end product of the pathway reacts with the first enzyme that is unique to the pathway. The reaction occurs at a site on the enzyme that is different from the active site, called the allosteric site. When the product binds to the allosteric site, the enzyme undergoes a conformational change and can no longer react with its substrate. There is no substrate for subsequent steps in the pathway, and the final product is no longer synthesized.